live. So we're going to just go. Okay, thank you. And to those of you online, hello. I don't know if there's anyone online, but we'll figure this out. So we're going to start. Mayumi has a question about homework 6. Homework 6. Yes.
Okay. So section 3, questions 61 and 62.
Mm-hmm.
I wasn't sure which one we're talking about.
Okay, let me find out.
Like which item, or this is overall?
61 and 62. Oh, this is with the...
How'd it
go? This is section 3 results. What is true about the following mean differences? Which of the following is true about the factor mean differences of these samples? So section 3 is the metric invariance. So looking at the invariance for intercepts.
Mm-hmm. But is this?
So that should be with respect to the kind of the final model itself, the last model that you ran.
Oh, okay.
And so.
And then so the last model output, and I'll just look at the student.
That's right. Yep. Mm-hmm. And then that was 61, 62. Which of the following is true about factor mean difference? Same thing. Yep.
Same thing. Oh, okay.
Cool.
Okay, and then 55, section 6, 55 and 56. I just didn't know how to read the output in order to answer this.
Okay, so let me go back to an example real quick to show. Yeah. Is that okay?
Mm-hmm.
I certainly feel like I've had a break in between class. I'm just not. I don't know about you guys. I am feeling. I'm like, we had class before? What? When did that happen?
So long.
Yeah. I'm going to go to the invariance example that's, this is example 7a, which does invariance in the same method you should have used in the homework, right? Mm-hmm. And if I go to the bottom of this example, if I'm looking at the difference in factor means, actually 7a is good because we have 2 factor means in it, right? We have 2 groups. So when we get down to this example right here, if we look at, so the depression intercept is 0 in this one, and it is 0 in this. This is when we constrain them to be equal. If you go through and you look at the model where you have these intercepts estimated, so like right here, or the means, the factor mean for one group is factor variance. We're talking about variance, pardon me. What is the difference between factor means? What is the test mean? So if we go, so now, let's back up here. In this section 5, you had to set up whether or not there was variances were equal or unequal. And what did you find in section 5 for your homework? Were they unequal? Should have been, I think.
Oh.
Okay. So, so to get to question 6, let's talk about question 5 first, because that's going to lead into what question 6 does.
Okay.
Or section 5. So, in this section 5, you took the model that you had with the residual variance before, and you constrained the variances to be equal across groups. And then you tested whether they were equal or not. So using the result of that, right, you can answer the next question with that model, the one that you preferred. I think it's going to be the unequal variance model.
Okay.
The way that you figure that out, the estimate of the difference between factor means, because there's only 2 means, and one mean is 0.
Yes.
Then the estimated factor mean is the difference between the 2.
So just minus, right?
That's right. If it depends on how I entered it. Yeah.
Like to subtract.
That's right.
Subtract.
Yeah. Either it's the number or it's -1 times the number, depending on which group is being subtracted from.
Right.
So
okay. I will go back and do it.
Let me look.
I think that's what I did, and then still just okay. Anyway.
So for instance, here in this example right here, if I take the last model I ran, in the looking at the factor variances, if I had here in one group the mean is 0, the other group the mean is negative
Mm-hmm.
0.091. That is because the first group is 0.
Mm-hmm.
If I take the difference between the two, you either get negative 0.091, right?
Mhm.
Like negative 0.091 minus 0 is that. Or you get 0.091, right? Which is 0 minus negative, right? So those are the two options for what to use there for that.
Yeah, so then both ones can be green on your system?
Yeah, it should be.
Oh, okay.
And then and the test statistic is then just the z value that goes right next to it right here.
Okay. I'll go back to Zoom once again.
Okay. Yeah, and if you still have issues, just email me. I'm happy to try to bring you.
No, not this one. This one. I was looking at the different one. Okay.
Okay. Other questions on homework 6? Is it giving you the impression of the that I told you, which is this type of analysis is very long and tedious? It's frustrating. Okay.
Okay, the test of statistics is a z value.
That's right. It's the one it's just in that same line itself.
Okay.
Yeah, so here's just the general philosophy for it. If you have the result where you can get a test statistic in a walled test, which is just straight from the output right here, use that. But if you don't have it in the output right here, and you can't just make it like with the colon equal in Levon, I could go and create a new parameter that was the difference between the two. If you don't have that, then the test statistic comes from the likelihood ratio test in the ANOVA function, right? So if it's directly in the output, look there, or if it can be put in the output, look there. But otherwise, go to likelihood ratio test. They won't give you the same number for a set of data that you had, like a finite sample. But in the limit, when you have enough data, they should give you roughly the same result.
Okay. Sounds great.
Cool. Boy, this is empty today. 5 students. Thank you, Lou, for coming. You represent 7 people in the room. All right. So, should we start? We're moving on from invariance today. You know what we're moving to? We are moving to, pardon me?
SEM.
SEM. Well, more SEM. We're moving to higher order factors and method effects. So basically, other ways that we can trick out our models to represent what we do. But again, it's still structural equation modeling. This is still more things happening in the analysis itself than just this typical measurement model that you'd see. And here I'm going to go to lecture 7, which is the invariance lecture right here. I'm going to open that in, open it in PowerPoint. There it is. Now I can draw on it, or at least we'll see if I can. What's new in PowerPoint? How about working? Oh, you know what? What's new is how about opening the file that actually, it was not lecture 7, it was lecture 8. I screwed that one up. There we go. What's new with Jonathan? Nothing. He's still the same POS he was before. All right. Here it comes. It's nice, huh?
So nice.
So I got to tell you, I know it's not the politically correct thing to say, but I'm not so opposed to global warming. You know?
Short term.
I think living in Kansas, I might start thinking of inventing, trying to think of how the crop change might be. Maybe buy some acreage, and as soon as we're able to grow oranges up here, kind of do that, like citrus fruit. No, it's not. I shouldn't say that. But you're right. Short term.
Short term is fantastic.
Yeah. No, it actually was cold. It got cold at the end of October, and normally as a Californian, I don't know if you do this being on the ocean or not. If it gets cold, I get really resentful. Like, just really like I'm entitled to above freezing weather always, right? Which is ridiculous, as I've been told many times. So I'm resentful. And then this year though, I was like, this poor Earth needs. I'm okay with it. We need as many cool days. The more of that happens, all right. I'll try to take the big picture.
That's what I feel every day.
What's that? We need
Yeah, in winter.
winter? Yeah, I'm resentful.
Yes. They're like, no, they need to be cold.
That's right. We need.
It's winter.
It's okay to be cold. It's
Yes.
part of the cycle of things. But
Yes.
yeah, like I'm rooting for this Indonesian volcano Mount Agung to spew like Mount Pinatubo did back in the 1990s, and where it cooled temperatures by I think it was like 1 degree Celsius over across the world for like a year. I don't know if you remember. Yeah. So
that's a long time.
yeah, but it was just somehow I'm like yeah there's more of that. Not to I'm like oh wait there's people it'll probably affect who live there, but globally,
Yes.
But I can't take one for the team. It needs to be warm here, right? So, all right. Okay, let's talk about higher order factor models a little bit. What is a higher order factor? It's if we were to just quickly describe it, you have, let's imagine a measurement model like this where you've got 3 factors. Right? My poor drawings, these are all supposed to be, imagine these are all identified, although you don't have enough items here, but to save time drawing. A higher order factor model would basically say, okay, there's 3 traits, trait 1, trait 2, and trait 3. Let's imagine there's some general trait that's measured by all 3 of those, right? So this is kind of like your higher order factor right up there, right? So you're saying covariation in these traits is really linked to some overall covariation in some even higher level type of thing, like this dynamic multiple process. Now, why this is a structural equation model, you'll note we have latent variables predicting other latent variables here, right? And so what you'll end up saying with this is that there's a direct effect, effectively, of this higher order factor model on each of the lower order factors. And then there's an indirect effect of the higher order factor on the items itself, right? And that's what we're going to get into in the next set of lectures, which is mediation that shows up. So that's what a higher order model is. Let's go through, remember the sequence again of steps in CFA or IFA. If you're trying to build a multidimensional model, a good way of doing so is to specify your measurement model. And then for each factor, break them apart, right? So if you can, if you have simple structure where items are only measured by one factor, do a measurement model for each factor separately. And the reason I say that, before putting them all into one, the reason I say that is because you cut down on a lot of places where model misfit happens if you do it that way. If you start with, let's say you have a 7-factor model, and you put all 7 in at first, and you see the model fits terrible, you can, add parameters and work on model misfit, but I feel like it's better to start with the model, each of the factors separately first, get good measurement of the factor by themselves, and then putting them together. Mm-hmm. Now, I will say, when you put your models together, when you go from like 7 unidimensional factors and you put them into one 7-dimensional structural equation or CFA model, it's possible that each one of those 7 that fit before now globally don't fit anymore. It's not guaranteed to fit because now you have these more intricate relationships. If you think of it, if the items are all separate for each of those, what the global model has to do is describe the covariance of the items in the data. And if your data went from 7 items or 4 items to 11, then there's extra covariances that may not account for. So I've found in my reading of the SEM books, this is the hand-wavy part of the whole thing, which is like, yeah, you should check the single factor measurement models first and then put them together. It'll fit. But what if it doesn't? Well, it's possible. Next. All right, so you still need to modify that structural model, the putting them all together at once.
I was going to say, like, which one should we start with in a practice? Should we do them separately or put them together?
I like the separate idea still better, and the reason for that is, if you can. Sorry, if you have items that measure more than one, it's
cross-loading.
Yeah, if you have cross-loadings, you're not going to be able to do that. But I like it better because it gives you a chance to kind of narrow the focus. I mean, if you think about it, if you're just measuring one thing, you really have to focus on what that means, right? You talk about what items show up, what does it mean to have different levels of the trait? It's like but when you put them all together, do you really do that same thorough process on each of them? And I don't know that it usually happens. So I like that first step on each separately. But from a technical point of view, I don't think it matters. Does that make sense? Like, there's nothing wrong with doing it all simultaneously.
Yeah, to me it seems like more organized when you do them like separately.
Yes.
If there are like very poor items, you can throw them away.
Exactly. Yes. There's nothing wrong though doing it jointly. Nothing wrong at all, like mathematically. You're not breaking any rules or anything like that. I just feel like the separate one sort of lets you focus a little bit more directly on the measurement process. Because at the core of all these models is, I think a lot of people in the SEM world forget it's measurement, right? We have this latent variable that doesn't exist. We're making claims about. We need to make sure that those claims have evidence for, right? But you can still have that evidence in a multidimensional model. It's just I feel like people, when they put that together, there's so much going on, you lose sight of it pretty quickly. So again, you specify your measurement models, and then you go and estimate them separately. And for each one of them, you figure out whether they fit, and you need them to fit. So you do the same type of information we typically would do. Look at global model fit, look at local model fit. You may want to quantify how much reliability or test information you have. And then once your single factor measurement models are good, then you can consider you put them into a big, large model itself. And if you're interested, you can think about the higher order structural model. Again, now you don't have to. This higher order structural model is just you may have a hypothesis saying that there's these 3 types of, or these 7 types of factors, but really they're all indicators of a big general condition going on or something along those lines. In my analysis of the gambling data that you're doing with your homework, we had 10 factors. We had, and they were all representative of the DSM criteria for pathological gambling. There's 10 different criteria. One is like I think about gambling often, or no, I'm preoccupied with gambling. One is something like I've stolen money to finance gambling. So, but if you read the text of the DSM, and I'm not a clinician, so Craig can probably point at me and be like, "Quit playing." I think nobody else in here is in an APA accredited program, so I'm gonna pick on you. You probably, but if you read the text, it literally talks about those 10 criteria sort of fall along the lines of 3 more general topic areas, which is kind of a disruption of lifestyle, kind of a disruption to your lifestyle, a loss of control, and then I'm blanking on the last one now. But anyway, there's 3. So we put a higher order factor model to it where we had those 10 factors, but they indicated, depending on which one they were, they indicated whether it was dependency, disruption, or loss of control. Right? So if you've lost your ability to control your impulses, or if you're dependent on a behavior, or if it's disruptive to your lifestyle. And so that's why those higher orders, we tested to see if that worked. Our whole paper for the gambling study, although we used a little bit different method than CFA, was to test exactly what the DSM was saying, that there's 10 of these criteria, and maybe there is a higher order structure.
Was there?
It did fit. It's not as clean. The model itself was not as clean as what we do here. We didn't have all the tools at the time we ran it. But interestingly, we got a sense there were 10 discrete things, but we didn't have a lot of variability on some of them. But then also the question, we had a different study where we had the DSM says that there needs to be 5 or more. You have to meet 5 or more of these 10 criteria, and which is, you think about it, it's a classical test theory thing, right? 5, which 5? Doesn't matter. 5 period, right? And so we looked at that, and that didn't seem to fit the data as well. Any 5 versus, right? So it looked like there were some specific ones that were more indicative of a problem, and which I think you probably, as a clinician, expect. So motivation for higher order factor model. I'm trying to motivate the factor model itself, and the factor model itself, you do find these occasional hypotheses. All these traits I'm trying to measure are indicative of something else, and I want to go and test that hypothesis. So really, what we're trying to do is look at what type of. If you think about this poor drawing I had here. If you look at one of the lower order factors, if that was your measurement model, right, you'd say these items all measure this factor, right? In a higher order factor model, the measurement model is right here, the higher order factor is being measured by each of the lower order factors themselves. Right? So they're effectively the data for this higher order thing.
The
Like
subscales,
exogenous.
not the items.
Mm-hmm. That's right. What's that?
Is it like they become the exogenous?
That's right. That's right. So, and now we're doing it simultaneously, but just think of it conceptually. What does that mean? Well, everything that you thought about for this lower order factor model now applies to this higher order factor model. All right? So we can take a look at the factor loadings. We can talk about identification. Right? We mentioned this when we got into identification of the factor before. If we were talking about how many items you need to be able to identify this, you need, for the higher order factor, you need 3 at least as a minimum to make it just identified. Right? So you need 3 lower order factors to make it just identified.
Which makes sense because by the end you just need the factor score.
But, and actually, we're not outputting anything. It's all a simultaneous approach.
Okay.
But the other thing that happens, if you remember in the factor analysis world, when we got into the measurement models for it, if we looked at the multidimensional measurement model, there was some Greek equation for the covariance matrix was equal to the factor loadings transpose times the factor covariances times the factor loadings plus the unique variances. Remember this equation from the... I put this up and only briefly talked about it. Basically, the factor analysis itself was trying to tell you what the observed covariances were like in your data, right? And it was using some type of math to do so. Well, this higher order factor model goes and grabs this term right here. This is the variance covariance matrix of the factors. And it does the same process on it. So it's basically saying, okay, I have this pattern of variances and covariances of my factors. Can I go and factor analyze that, or put a factor on that itself, and describe that pattern of variances and covariances? So that's sort of how it's working. Which higher order factor structure best accounts for the covariance amongst the measurement model factors, right? So now remember, this is not the items, this is the factors themselves. So this is also called a structural model. In the context of structural equation modeling, I briefly mentioned it before, but it's going to be much more relevant this last 2 weeks. There's the measurement model, which is where you have the lower order factors in the data, right? The relationship of observed data to factors. The structural model is the distribution of the factors, or the relationship of the factors itself. So the higher order model, because it's only talking about the latent variables themselves, there's no data involved, there's nothing observed with it. It's part of what's called the structural model. How are we doing? Okay, so the best fitting baseline, so just like you would expect in your real data, remember the baseline model that we used in the factor analysis? It was the one where we estimated every covariance. The best fitting data in the model in the higher order sense is where every covariance of the factors is estimated, which is the one you started out with in CFA, where we estimated all of them. So you think about it, that saturated model in your CFA world is saturated for the structural model, because the variance covariance matrix of the factors is now what we're concerned about. And when we put the one factor in, or we put the higher order factors in, it's going to make it not fit as well as. It can only fit as well as. It cannot fit better, right? The fit can only get worse, really. Equal to or worse, because we're reducing the number of parameters that are in there in the saturated sense. So, so how would you figure this out? Just the same way that you would look at if you had a covariance matrix for your items. Remember how we said, oh look, if the covariances were all about the same size, that sort of indicated the same type of pattern of factors, or there was patterns to it. Patterns in the covariance matrix of the factors indicate whether or not there's a higher order factor present or not. So what I will note is the distinctions between CFA and IFA and all of the other measurement models. Remember, CFA for continuous data, IFA for categorical ordered data. Everything else that we couldn't do in Lavon now, but could in theory do, like count data or whatever else. Once we're dealing with the factors themselves, those factors have always been normal and continuous. So we don't need to worry about the type of measurement model we have. This applies whether you're using CFA, whether you're using IRT, whether you're using something that doesn't even have a name. All this same process still applies. So So what do we have to do to scale the higher order factors? We need to, by scaling, what I'm talking about is how do we need to identify the variance and the mean to make this model work? And what we need to have, because for each one of the lower level factors, we need to have an estimate of the factor variance. We need that because if you think about what this higher order factor model is doing, this arrow is implying that factor 1 here is equal to some linear function like a beta 0 plus beta 1 of the higher order factor plus error. So it's a regression line of the factor itself. Error has some type of, I guess it would be sigma squared up here. We need a variance for it because when we predicted if this beta term right here is significant, this variance is going to shrink. It's residual variance, right? It becomes smaller and smaller and smaller if the better the prediction from the factor gets. So we need that variance to be estimated in our factor model. And the way we estimate it is most commonly a marker item. We set one of the factor loadings to 1. Now, we still can use the z-score for the means, where we estimate each of the item intercepts separately. So that's fine too. So here are some options in identifying the 3 factors. So if we had 3 lower order factors here, what we can do with this, if we wanted to think about whether or not we needed to have, if we could have a higher order structure model, let's take a look at the way we talk about the number of items needed. And this is sort of relying on what we talked about way back when we talked about CFA. In a CFA measurement model, what we'll have is, since we have 12 items, we know that the saturated model has 12 times 13 divided by 2 over 12. This is the number of covariances. These are the number of means. So they have 90 possible parameters there. Our 3-factor model actually ends up giving us 33 parameters, so we have 57 degrees of freedom. And because that degrees of freedom is bigger than 0, it's over-identified, so it's okay to estimate. Now think about that same approach, but instead of looking at the items here, let's look at the factor level here. We have 3 factors, which are now our items. Right? So the 3 factors are going to have how many variances and covariances do we have? Well, we're going to have 3 variances, 3 covariances, right?
1, 3, 2, 3.
Right? What's that?
Is it 1 like 2 and 1, 3?
That's right. Yeah, 1, 2, 2, 3, and 1, 3. Yeah. And we have 3 variances, 1, 2, 3. So there's the 6. That's 3 times 4 divided by 2. There's 6 variances and covariances. But we didn't estimate the factor means. We have actually 0 of those left. So there's a total of 6 parameters maximum we can have in this model. Right? If we were to put a higher order factor on it, like this, right here, what would we be estimating? Well, we would be estimating 1, 2, 3 factor loadings, 1, 2, 3 factor variances. There's our 6. Right? So here it is right here, actually. Right? So what that means is,
which is okay.
Just identified. That's right. Has 3 degrees of freedom. So what you end up having, if you have 3 factors, is that if you believe there's a higher order trait, this higher order trait model fits perfectly to your data. Just like when you had 3 items, your factor fit perfectly. And so remember that argument you're making. You're saying, no, I have a higher order trait. It was the same argument you're trying to make for, no, I have a factor with these 3 items. It's a weaker argument because you're not actually testing anything. Your model is equivalent to a model where there's no trait. There just happens to be 3 correlated items. Right? So that's a key distinction here. If you believe there's a higher order trait, you're not actually testing it here because there's another model that fits equally well that's just as plausible, and you can't actually discriminate between the 2. Yeah.
This is the most common, or one of the most common statistical reasons in education, right?
One of these types of models here?
I mean, it's always like higher orders.
We do see them a lot, but I don't know. I don't know if it's common. Like if you think of what we do in educational measurement, like an IRT model, we rarely have more than one factor. So there's rarely anything ever to talk about for a higher order trait. So I don't know, but I do think you see this a lot. I don't know. Honestly, I don't know where you see this. Have you, anybody in your research seen this?
I see it a lot in EdTech. When
EdTech,
they measure,
okay.
Like the overall satisfaction of LMS, learning management system.
Okay.
There are like multiple factors to measure like one.
I see. Okay, so yeah, that may be the case.
Or like usefulness.
That may be the case then. Here, so this is a method where we estimated all the 3 factor loadings. So that means we had to set the factor variance to 1 for the higher order factor and the factor mean to 0. But we could also identify that higher order factor with a marker item by setting one of the higher order factor loadings to 1 and then estimating the variance. And again, it's still just identified.
Can I say
Yes.
the lower order factor is like a mediator between high order?
That's what you could say. The low order factor mediates the relationship between the higher order factor and the items. Although the typical thing we'd want in the mediation is a direct effect between the higher order factor and the item itself, and that doesn't appear. So it's mediation, but it's not a... I would say that's only recently have I heard people describe it that way, and that's because mediation's become a big deal to some people. So, what do you think of mediation, Lou? Sorry, Lou. It's as Lisa says it. My wife says it's a regression with a better marketing campaign, right? So I think the only reason when I was in grad school, mediation was big, but it wasn't like the mediation of today. And I never heard anyone describe it as mediation. But yes, there's an indirect relationship of this times this. Bless you. So, okay.
Wait, so you're saying that nowadays mediation is more a bigger deal than
It seems like it's blown up.
in the past?
Yeah.
Which is path analysis.
Yeah, it is. It's path analysis. It's describing relationships between, multiple variables simultaneously. But yeah, I feel like now in certain fields, and the fields I'm fairly close to, like social psychology and parts of social sciences, you see mediation a lot these days. Whereas I didn't see it a lot when going through grad school, but maybe it was just because we're focused on quantitative stuff. Yeah.
When can we talk about the invariance here? Would it be for each factor?
Yeah, if you're doing an invariance model here, you have to do the whole way through. Right? So you have to have invariance not only on the measurement model, but then you got to do invariance on the structural model as well. Right? Yeah. So invariance, it becomes even more complicated then. But the same process would hold. You just have to work on the measurement model first while holding, the factors to be different, and then slowly constrain parameters moving your way up the process.
So you do the invariance with each factor first?
Yeah, you do the measurement model invariance just like we did before, using the factor loadings on the items. All right.
Okay.
And then the intercepts on the items.
In lecture 7.
That's right. They still do that, but when you get to the structural invariance, instead of testing factor variances where you tested where each of these were different, you just basically start over again on you take the look at the factor loadings and see if they're invariant.
So we can
structural
do the
model.
invariance only with the factors, not the items.
No, you have to do the invariance of the whole thing.
Okay.
No.
That's gonna be a lot.
Yeah, it's the invariance of the whole thing because again, the same thing will happen. Item level differences are going to permeate through, and if you don't control for those, whatever you find for differences in the factors might be due to
The
items themselves rather than actually difference in the factors.
Which is gonna cause like some error there.
Absolutely. It would cause a lot of different conclusions to be made. Potentially can cause that to be made. So
Is it common to do invariance and describe each item?
yes, I would say
That's a lot.
it's a lot. I don't know how common it really is. When I
Is it necessary?
well, if your goal of your study is to describe a factor difference across groups, yes, it is. It depends in which field you're in if it's necessary, because some fields haven't discovered it yet, or the people aren't doing it yet. Right? It's an interesting thing, right? So you get Methodologists, the methods from this invariance came from psychometrics. Generally, people in quantitative psychology, but also people in sociology, some in education. But it slowly trickles through fields, right? And if you're not in a world in quantitative psychology, we're not dealing with data very much. We're dealing with models. People who deal with data don't typically read the literature for it, so they have to somehow get trained on it, and it takes a long time to trickle through. So yeah, depending on the journal you're publishing in, depending on who the editor is, and whomever is going to read that paper, the associate editor, the journal reviewers, and so forth, they may not believe it's necessary, or they may believe it's even something you shouldn't do, but mathematically, yes, I think it's necessary, and it comes from actually mathematically, but philosophically. You're going to make a claim about whether there's a group difference on the factors. You have to make sure it's truly a group difference. The only way that you can tell that is by testing measurement and variance across. It strengthens your argument for it. Because nobody can say, but, what if it really was these two items that were causing? Well, those two items don't mean the same thing across yours. All right, well, it's not really a group difference then, right?
But if you don't add gender, for example, like as a variable, they cannot stop you from publishing it.
Right. Yeah. If you're not looking for group differences in the factor, you're not. That's not typically thought of where we have to worry about that.
I have a more general question.
Yes.
For the group difference, if I apply the model into the poor data, it maybe model fit is bad, but do you model for separate group within group, it will be model fit will be good.
Okay.
Is that possible?
Yeah, it could be possible, but when you do this, so when you do like the configural model, and you have bad total fit but separate group, it's good.
Yeah. If I didn't do measurement invariance,
right?
I found the bad model fit, but it's because I didn't find the group difference in my data.
Oh, right, yeah. I don't know the answer to that. I think there might be cases where that could be the case. I will say that, you can, if you're talking about the model chi-square, like, your chi-square term, you can, because in the configure model, those are additive. You can see how that works. I think there may be a case where you can, so then the other model fits is like RMSEA, CFI, TLI are related to chi-square, but it's related in an odd fashion. And when you pool them together, depending on the number of people in each group, you may be able to find it. I don't know, though. I'm sort of speculating without actually a firm answer for you. So I'll go with a firm I don't know. It's possible, I think, to have good model fit in the groups, but then putting it together maybe not so good, or vice versa. So
yeah, I'm doing a project to want to find identify some group difference, but I don't know which is a group will make the model fit better. I know the global model fit is moderate, but I want to identify separate groups which will make the model better within group.
Well, that's a little bit harder. So describing how well a model fits within a group, I mean, you could run a model separately and get that. But then the comparison is a little bit harder. I mean, there are absolute measures of fit, so you should be able to go compare CFI and TLI against each other. Okay. But there's no real analytic test for it. And so it's not really as easy as just looking at the numbers. If you really want to have, I guess you could bootstrap and randomly sample within group and then come up with the distribution of each of those and talk about the proportion of times one's better than the other. But
yeah, I also looking for like latent class, maybe.
No, don't even get involved in that. Yeah. What do you think about latent classes, Lou? Sorry. Yeah, the latent class idea with this is no. What happens with latent classes, particularly if you want to understand what the classes mean, you have to make sure that the data for one class model fits it perfectly. And the only reason for that is if it doesn't fit perfectly, you'll always extract more classes just to fit the data better. It's not necessary whether there'll actually be people there, but in a latent class model, the only way that you can make a model fit better is by adding another group of people, because you get this whole replicate of the whole model one more time. And So if your first model doesn't fit very well, you will almost certainly get more classes. Those classes most likely will be spurious.
Okay.
There's some papers in the early 2000s. Dan Bauer showed this in the factor model world. And then, like in IRT, for instance, there's people who go around with a mixture version of an IRT model. A lot of times they use a mixture Roche model. Remember the Roche model has one parameter? So I did I had a person I was working with. She was a postdoc, and she said to me, "Hey, look, I did this mixture Roche model, and I found these 3 groups of people." And I said, "I doubt that," because I'm that way. And I said, "No, what you found is because the data, I knew the data she had came from a large testing program. And they usually use a 3PL, 3-parameter model, and then they discard items that didn't fit the 3-parameter model. So they sort of purify that it's going to be a 3-parameter model. Well, she went and fit a mixture Roche model to a 3PL, which clearly won't fit because the curve, you know, the 3PL is the asymptote, right? The asymptote, that little curve S-shaped function is a non-zero asymptote, whereas the Roche model comes down and has to go to 0. But not only that, the slope of the lines can be different in the 3PL versus the Roche. So we did a little study, and we had a simulation study where we had 30 item tests we generated, and we generated it with like a 2PL and estimated it with a mixture Roche model, right? And so we generated it where we generated the data where we had 29 of the 30 items fit the Roche model. We allowed one item to not fit the Roche model, to have a different threshold, a different slope, excuse me, different loading discrimination. And sure enough, extra classes showed up. Right? We didn't generate the extra classes. We generated one class of data. There was only one group. We just generated a model that didn't fit the one class model, and extra classes showed up. And so the reason why I'm saying this to you is if you're interested in describing what those groups are, you have to be very careful that the groups are real. Whereas I know Lou this morning was talking about multiple groups, but you're not interested in the groups. You're using those as a means to an end to get something else. So the cool thing about that, actually, if I could show this, now that I have you here, let's see if I can find it. Oh, my picture needs to change. Let's see here, where was it? There it is. Spurious latent classes in the mixture Roche model. Grab it real quick. There's a great way we try to summarize this in a picture, and I think it sort of tells the story. If you ignore the class, if you sort of aggregate across classes, let's see if I can find the picture. Sure enough, the aggregate is it looks like if you draw an item characteristic curve from it, if you draw the S-shaped curve, sure enough, it looks like a 3PL. There it is, right here. So here is the 2PL. The Roche model is right there. And then the 1 and the 2 mixture Roche model with 2, let's see here, 1 class Roche, 2 class mixture Roche models themselves. So hang on, that's item 1. There we go. So what you're getting at here is this dashed line right here. That's the curve after you fit 2 classes. But if you fit more and more classes, if you had like 200 classes, that curve is going to identically look like the original data's curve. We would call that what type of parametric? What? The semi-parametric model, all right? Which I didn't know the language for back then. So point being, be careful of latent classes.
But bootstrapping isn't recommended either.
Bootstrap, it's a generic way to try to get a sampling distribution of parameters. So in the case, if you were to say, I have 2 groups that I know who they are, and I can go find 2 different CFIs. Let's take a model fit into CFI, right? So group 1, the CFI is 0.07, or sorry, 0.9, and group 2, the CFI is 0.92. Well, group 2 has a better model fit than group 1. Well, is it always the case? We don't know. So the bootstrap is a way to randomly generate data sets and then go and get a sort of a distribution of CFI for the 2 groups, and then you can sort of say, yeah, the probability that group 2 has a bigger CFI is whatever, but I don't know. So Okay, well here's what happens. Going back to our analysis here, this is a problem I've seen happen a lot, where you might think there's a higher order factor, but you really only have 2 lower order traits, right? So here's a higher order factor with 2 lower order traits as well. So there's 2 higher order factors. This model is not identified unless you make some type of additional constraint on the factor loadings or the factor variances or both, right? So this is a problem. I've had this happen a number of times with people who have consulted with, saying, you know, theory says this should be the case, and it's like, well, how are you going to test it? They can't. They go and they identify it by making the factor loadings equal, or making the factor variances equal. It's like, well, you're not really doing anything different than having the 2 factors by themselves, right? So it's not a testable hypothesis. So just like so how do we figure out how many number of items we need, or how many factors we need? It's the same rationale we used for our data to figure out how many items we needed to measure a lower order factor. In the higher order model, now it's how many factors, lower order factors, are needed to identify the higher order model. So it's like CFA on the higher order things. So 2 is right out, 3 is perfect fit, so that weakens your argument whether it's actually there, but 4 is testable. Right? So, and I would say, technically speaking, there are permutations of testable versions. If you have a higher order factor that's measured by 4 and another one that's measured by 2, you can get away with that if they're correlated, right? There's certain combinations of these that will be allowed, but you have to work through the math on it to figure out. So this is hypothesis testing that you typically say. Do I have a higher order factor of my subscale factors, right? So if you have 4 or more, right, you can actually fit this estimated. But otherwise, if you have 3 or fewer, you cannot determine it. And actually, I think that's where I can pull up the example here. If I go to example 8, let me take a look at it. What's that? Did I do something wrong? I always do something wrong.
I like the rhythm.
What's that?
The rhythm.
The rhythm? Oh yeah, I'm bouncing back and forth. Here, should run this ahead of time. Sorry about that. Here, what we end up having is there's a 5-item. There's a factor model where we have 5 different scales. There's 49 items altogether. And we're going to do CFA with MLR and IFA with the weighted least squares. So basically, we're going to compare both approaches, one using the ordered equals in the Lavon syntax and one without. What you're going to see here with this, though, what I'd like to show you is, of course, things aren't going very fast. What I'd like to show you is that to build the model for this itself, it's not that much harder. It's not that much more syntax than you already know. Okay. Oh, why are you working so slowly? No, here. Tell you what, we're going to go over to the HTML version of this, because I do have that already built. Okay, so here, what you'll see in the very first part is there's these 5 factors. These are college students self-reporting on 49 items assessing childhood maltreatment. This is, how do you remember things were in your childhood? And there were 5 types of mistreatment you could have, about ways that you were neglected somehow. You could be spurned, so there's a spurning factor, which is where we had verbal and non-verbal caregiver acts that reject and degrade the child. You can be terrorized, which sounds terrible, where you're threatening someone. You can isolate a child. You could have corrupting behaviors, or you could have you just ignoring. And so this first set of factors you'll see right here were to test whether or not we had good model fit, and sure enough, this is sort of testing the unidimensional model for each of the 5. Then we go and put all 5 together, and what we get is Oh, it's not showing me that. Oh, there it is. Okay. We put all 5 together into our big model. Here we go. We put all 5 factors in. We can then add a higher order factor, a higher order abuse factor. And the way we do that is to take, just like how we define a factor previously, we take the name of the factor, in this case abuse, equal tilde, and we put the name of the other factors that we've defined after the equal tilde. So like these were items.
The factor score.
That's right. And so they're factors themselves. Try not to call them factor scores, because they're not. It sort of implies that we're going to output them and then do factor analysis on them, which we're not going to do. We just call them factors. The lower order factors is probably a good way of putting it. So when we say spurn, once we've defined the factor spurn, we can use the word spurn in the analysis just like it were a variable we've observed. We cool?
What's P06? I mean, P.
Those are all the names of the items. The P,
items.
yeah, the
Okay.
P starts with P for whatever reason.
Okay.
So now we look at our output.
Question.
Yes.
Do we say like 49 items?
There should be, I think, 49 items.
Okay.
I don't have an exact count for you.
Like in the top.
It says 49.
Yeah, it says 49 at the
So
top.
these are like more items or what?
Yeah.
The P57 and P51.
No, there's, yeah, the
Just-
data set had more than the final paper gave, yeah. Mhm. So yeah, there was a bigger item pool, but not everything
It's
fit.
just because in the beginning it says 49. That's
Right,
why
so the final model has 49 items in this, but
To start with.
the data set may have had more, or they may be numbered in different ways.
Okay.
So what you'll see here, at the very beginning, we ran the model where we just had 5 factors with no higher order factor. And we estimated that I didn't output the results. But then I ran the model that has the same measurement model, the same here, but now I add the abuse higher order factor to it. And here's the output from it. Again, it looks like the same. One thing we'll note here, the CFI is not great. TLI is not great. The RMSEA does look okay. All right, so at least there's some argument to be made. But now when we look at the output, what we're going to find is, under the abuse factor, this is the higher order factor, you'll note we're using the marker item technique. These are the factor loadings of the lower order factor. Basically, how well the abuse factor predicts the lower order factor itself. These are the factor loadings for it, right? So these are the unstandardized loadings over here, and then the standardized loadings are all the way over on the right-hand side. And similarly, we will have intercepts for each of the factors like we did before, but now we have one for the abuse factor, which is set to 0 by default. And again, we will have variances. Now we will have factor variances that we saw before. Sometimes we call these factor disturbances, which is adding more language that doesn't need to be there. Right? It's a variance of this factor. And we will see there's an overall abuse variance as well, because we had the marker item for each of those. And finally, under the R-square column, each of the lower order factors now appears. You didn't see this before because we didn't have anything predicting them. But what this model is doing is it's telling us that abuse is predicting, this abuse factor is predicting each of the lower order factors. And so because of that, these variances are residual variances. And therefore they have an R-square that goes as well. So that's what shows up. It's just like you would typically see in your analysis. The question you have to ask, though, is does my higher order model fit as well as my saturated model for the factors now? Right? So we can compare the fit. If I go all the way back here, my CFA no high and then my CFI higher, right? These two models I'd like to compare the fit of.
Okay. Higher, the first one is the saturated.
All right, CFI no high is saturated in the factors. Right, so if I were to show you this output right here, you would see covariances between each pair of those factors. or there would be a total of 5 times 4, 10 covariances and 5 variances in this model for the factors. So actually, let's count it out. Because we have 5 factors here, we're not estimating the factor means, so there's no factor means, but there are 5 factor variances, 1 for each, and then 10 covariances between the two. So 15 total parameters in this model for the factors. Now, what about for this model for the factors? Right? Well, we're going to be estimating 5 factor variances, or residual variances in this case, and then 5 factor loadings, 1 for each of these. Actually, pardon me, 5 factor variances, 4 factor loadings, because the factor loading of the first one is set to 1, and then we're going to estimate the factor variance of abuse. So 5 plus 4 plus 1. So there's 10 parameters now. So the model that has no higher order syntax had 15 possible parameters. The model with the higher order syntax has 10. So when we do our likelihood ratio test, what's our degrees of freedom for the difference? 15 minus 10. So you should see 5. So we go down. The way we do our likelihood ratio test is the way we've seen it all along, the ANOVA function. We put in both models. We see our degree of freedom difference is 5, the way it should be. And we see a minuscule p-value. What does that indicate?
Not good fit.
Not good fit. That means the model that has fewer parameters does not fit as well as the model with more parameters. So if we were to say, is there a higher order abuse factor in our data? The answer from this likelihood ratio test would be absolutely not. The abuse factor does not fit these data as well as having a general correlation. So it's like saying there's no one type of abuse. Right? These are 5 unique types of abuse themselves. So. Another thing you often see is you can compare the multidimensional model with the model that has multiple factors, and you can see if that fits well. But I don't want to talk about. The same thing happens if you wanted to look at this with the IFA, using the ordered equal statement right here. So if we treated these as categorical items. So now what you find is, again, the model fit comes out. You have the same output. You have the same, actually this is all the factor variances and covariances. It goes on forever. So we have thresholds for everything. Here's the higher order version of it. The higher order version has factor loadings. And we just go on and on and on. And whether or not it tests, oh, look at that. I tried to test the model fit and Levon blew up. And that's the problem with Levon. It's not giving us the right number.
I have the same error message for my homework 5.
Uh-oh. That's a problem. I don't know how else to compare fit there. If you send me your syntax, or if you let me play with your data, I might be able to try to make it work. I'm not sure we can come up with it.
Okay.
Because this shouldn't happen. We've had control over what the constraints were, and it's giving us an error. This is part of the beta version of Levon. We're sort of pushing its limits, unfortunately. So
what do we do in this case? If this happens.
Throw up your hands. No. You don't want that. I don't know a good solution right now. One solution is to find a computer that has M+ and do it in M+, which I hate to give you to do. Another solution is to
using CFA. Wait, no.
You could use CFA. I mean, why not use CFA? You would work with CFA. If you have to go with CFA, go to CFA. That's another good solution. I don't have a good solution other than that right now. I don't know what I can give you to do. I'm trying to think of a way to give you the diff test, but it's really hard to do directly. So CFA probably be the way to have to go for this, unfortunately. Right now. I'm sorry. sort of one of the problems with Lavon is that we run into these situations where you're like, ugh, so close. So, let's see here. How about methods factors? Well, there's other different versions of factors we can put into an analysis. For instance, this is an example of life orientation by a paper in Psych Methods by Alberto Medu Alvarez and Donna Kaufman. Let's see here. They actually came up with something called a random intercept factor, where basically they said, actually, hang on one second here. Well, we talked about methods effects before, but let me see if I can do this. What we end up having here is 3 positively and 4 negatively worded items below, right? We have 3 positive terms down here. We have 4 negative terms. We mentioned how to handle this before, right? Remember we talked about the methods factors previous to this? We had to go and put a new factor on it, where the one factor model was optimism across all the items. But perhaps you might have an optimism, which is for the positive items, and a pessimism factor for the negative items, right? So that was one way that we could compare the two itself. Another way that we could do this, and this is, I know we talked about this in the CFA part, right? How would we go and come up with the method of factor? One was a general optimism factor, but one was specific to positive things, and one was a specific to negative ones. This is a model called the bifactor model. Now this has shown up a lot recently in educational measurement, I will tell you that much. The bifactor model is a model where we say there's a general factor itself, and it relates to all the items, and then there are specific factors that relate to only some of the items. So each item is measuring 2 different factors themselves, right? Each one has a cross-loading. This model, what does this represent? Well, the other thing that's interesting about this is, to make this work, we often don't see a correlation between the general and the specific factors. So
we do not often see it.
No, we don't, which is a really hard thing to explain. Why is there no correlation between these? You would expect them to be highly correlated. And the reality of it is, in certain models, it becomes unidentified. Right, depending on how you specify the model itself. Now, I don't have the math behind that, so that's a weak statement for me. I don't give you the right evidence for that right now, but see how that works. So yeah, you see this often. It fits the data very well. Another method that you could use, this is what was called a random intercept factor model. It was supposed to allow for constant person shifts across items. So maybe you look at the response scale and people interpret category 4 differently, but within a person it's consistent, but across people it might be different. Right? So what would you do with that? A random intercept is a term we borrow from a multi-level model. And by the way, all factor analysis models are versions of multi-level models. So we can actually trick out a multi-level model using factor analysis to make it work. And one way that we can do that is to create a factor where all the factor loadings are set to 1, but we estimate the factor variance here. Right? That becomes a random intercept, because when the factor loading is 1, let's imagine what this equation is. I1 is equal to our item intercept for the item plus our loading times optimism plus, now it's a 1 for the loading times the random intercept for a person. This is a person right here. And then plus error for the person and item, right? So when you do that, when there's just a 1 here, the factor score itself, the latent variable, becomes its value gets entered into the model equation almost like a constant. And so that person's intercept effectively shifts by the value of that factor itself, right? And so for every item, because this is a constant, for each person, each item's intercept is shifting up or down based on it, right? So that is what we're getting from it. Now, the random intercept is not often not thought to be correlated with the optimism factor, because again, it's an idiosyncratic property of the person interpreting the scale rather than something to do with the factor itself. But this is one way that we see this sometimes. And then there's the Heartland Forgiveness Scale, which Lisa was part of with Rick Snyder and Laura Thompson way back in the over a decade ago. God, we're getting old. This is happening. There was a series of factors where they had something about self, something about forgiveness for self, forgiveness for other, and forgiveness for different situations. But within each factor, there were three items that were worded positively and 3 that were worded negatively. And so we saw this example in one of the example 4 for CFA with one of these factors. I think it was situational forgiveness, where we looked at that. But the model that you have here is effectively coming up with 2 factors for each of these situational forgiveness. There's self-positive, or there's self-positive, self-negative, other positive, other negative, situation positive or situation negative. Or there's this right here, where you have a self factor, this is a higher order model, which is harder to see because you have a higher order factor that's of self that's related to both self-positive and self-negative, and that's only two for it there. But now we have a positivity factor that's a higher order that takes the self-positive, other positive, and situational positive and uses it, and a negativity factor that does the other. So where am I going with this? It's overwhelming, but you can be creative in how you try to make a model fit. So what would you interpret this as? Well, when you look at this, there's a bunch of what we're really after here is how well a person forgives themselves, how well they'll forgive others, or how well they'll forgive certain situations. And because of the way the items were worded, with the positive and negatively worded, that this model didn't fit, right? Or the model where you just have a single factor for each of these. And so what Lisa tried to do is say, okay, well, what if I broke them into the positive worded and the negative wording, and then I went about doing something like this, where I had a higher order factor that really represented something with self, something with other, and something with situational. And then I had a lower order factor with these. Now, believe it or not, this is actually an identified model. And the reason why it's identified is because if you look at it here, there are, with 6 different methods factors right here, there would be 6 variances, right? And how many covariances? It would be like 15 covariances. So there are 21 total parameters that we could have. But when you estimate these values of positive, negative, and self, we end up with a total of 18 model parameters. Now, she constrained them to have uncorrelated wording factors. So the positive and negative were uncorrelated. But I believe she allowed these there were correlations between the self, other, and situational. So what this is really trying to get back to is that original idea behind the instrument, which was there's 3 types of forgiveness that people might exhibit: self, other, and situational. But because of the way the thing was created with the positive and negatively worded items, you couldn't see that unless you went and controlled for positivity and negativity. And so when you controlled for positivity and negativity, you no longer had you had a self-positive and self-negative, so she had to create a higher order factor for self and a higher order factor for other, and so if you were thinking about this, you'd say, yes, there really are 3 factors, but to get at them the way the survey was designed, we really have to control for the positive and negative, which makes you not want to use negatively worded items ever.
This is why I guess it's important to spend a lot of time on writing items.
That's right. It is. It really is. And I mean, historically, we've been told, yeah, put some reverse-coded things in there, but they screw up every analysis.
You said this is just identified, so you mean just...
Actually, this is over-identified. Yeah, it's over-identified because the degrees of freedom is positive. So this is an okay model. This is a testable model itself, where you end up getting that. Now, there are certain equivalencies across models, which is going to make your head hurt even more. So what we're doing is reproducing the covariant means, the covariance matrix means the items. That means that models that predict the same version, that produce the same version of predicted covariance or means, are going to be equivalent models. And here's an example, right? Imagine you think A predicts B and then B predicts C, right? Well, this model gives us the same estimates as this model, C predicting B and B predicting A. The pathways are backwards. And this is part of the problem with mediation, with cross-sectional data, is that how do you determine the instantaneous effect of one variable on another, or better yet, the indirect effect of one variable on another? Generally speaking, it's very difficult. You have competing models that will fit identically. So sometimes it's very hard to do this, but just realize it's possible. Here's some more equivalent models. Let's see here. If we had depression being measured by 3 variables and then being predicted by 1 variable, right? That's equivalent to having depression being measured by 4 variables. Ouch. All right? Which is also equivalent to taking one of the other variables out and making it predict depression. Right? So you see what I'm saying with this? Right? You're saying, here's my measurement model. I have this latent variable depression, and I'm going to predict it with, I don't know, some observed variable. Well, this model is equivalent to saying, no, really, I'm taking depression and measuring it with a 4th variable itself. So what you end up getting here is that you really can't necessarily get the truth about a model, because there might be plausible models that are out there that mean something different, but are fit equivalently. So this is sort of where the word causal gets thrown around. Oh, this is a causal model. Well, we're trying to limit the number of ways that this model can cause the data, and it's tough to see exactly what that happens to be. Now, there are ways that you can sort of limit this from happening. You kind of know some use cases for how that happens, but it can be the case. Someone says, well, but isn't that equivalent to this other method? And you may have to say, yes. Yes, it is. So we're getting into that. But the next 3 classes, we're going to talk about mediation and structural equation modeling for real. Finally. But today we talked about measurement and structural models being 2 separate things. Measurement model is for the covariances amongst the items, and the structural models for the covariance events, the latent variables. That we also talked about, we need to figure out the measurement models, then do the structural models, right? And then we need to figure out whether or not things are unique. So that's it. Hooray! Right on time. All right, I'm gonna stop the video online, and if you have questions, come find me, or stick around, and I will talk to you.
Yes, I will stick around to talk about this ANOVA.